Hello, everybody. Welcome back. We are going to get started on chapter 2, which is chemistry of life. Okay, so the basic structures of life. Matter has mass and occupies space. Elements are a pure substance. We cannot break those down further. So examples of that would be hydrogen and oxygen. And then when elements come together, at least two or more, that's what becomes a compound. So water would be an example of a compound, as that's hydrogen and oxygen going together. All right, so particles make up atoms, which make up elements. So the three particles are protons, which carry a positive charge, electrons carry a negative charge, and neutrons are a neutral charge, no charge at all. Okay, this is a diagram of an atom. You'll see the nucleus in here has the protons with a positive charge, the neutrons, which carry no charge, and then the electrons float around out here, which is known as the electron cloud. So that cloud has different shells or ring. The inner ring can have 2 electrons, while this outer ring can have 8 electrons. You see the electrons have the negative charge. So based on how many protons versus how many electrons, that'll determine the charge of the atom. So if you have an equal amount of protons and electrons, then you will have no charge for that atom. Take a look at the link down here if you want to see a little bit more of an animation of that. Okay, atomic number and weight. So each element has a unique number of protons. That's what gives it its properties and makes it an element. The atomic number is the number of protons in the nucleus, and that's found at the top here. So in oxygen's case, that's 8. So oxygen has 8 protons. The atomic weight is found down here at the bottom. So that's measured in atomic mass unit. So you get the atomic weight by adding up the number of protons plus the number of neutrons. Those are each given a value very close to 1 atomic mass unit. So in oxygen's case, 8 protons plus 8 neutrons give you the almost 16 there. All right, isotopes are a bit of a unique case. So like we just said, the protons is what is the identifier for each element. So all atoms of the same element contain the same amount of protons. And most of the time they have the same amount of neutrons, but it's possible for that to vary. And remember, neutrons don't have a charge to them. So even if it has a varying number of neutrons, its charge will remain the same. So when there is that variation in the number of neutrons with the same amount of protons, we call those atoms isotopes of one another. I think page 20 it is, has a good example of that concept. Yep, page 20. Okay, that brings us to our first practice question for this lecture. Water is made up of hydrogen and oxygen. What would you consider these individual components, as in hydrogen and oxygen? So A, compound, B, element, C, matter, or D, atom. So take a second, think about that one. Okay, the correct answer would be B, element. So remember, a compound would consist of 2 or more elements. So water in itself, that is a compound. Matter is any substance that has mass and occupies space. So not quite the right answer there. And then atoms are particles that make up elements. All right, so talking about chemical bonds, we'll be discussing 3 different types. You have ionic, covalent, and hydrogen. And kind of the whole reason that atoms bond with each other is that they want to be stable. So we talked about the outer ring of electrons earlier. If it's full, kind of has a full 8 for 8, then that would be considered a stable atom. It's happy. If it has less than 8, then it's unstable. So it's looking for a way that it can fill that outer ring. And there's a few different ways that atoms do that with each other. So the first one we'll talk about is an ionic bond. So in this case, an electron actually transfers to another atom. So you see this lonely electron out here on sodium will transfer to fill this outer ring on chloride. So because sodium loses an electron, chloride gains an electron. It gives sodium a positive charge. That would be also considered the cation. And then you have chloride with an extra electron will now have a negative charge, and that would be considered the anion. So now that they are charged, the positive and negatives attract one another, and that forms an ionic bond. So compounds that ionize in water, that means that their ionic bonds break when they're in water, and they create a solution that can conduct electricity, and that is known as an electrolyte. All right, covalent bonds, these, rather than transferring from one atom to another, they're shared between atoms. And so they're a good bit stronger than ionic bonds. And that's why they're used for a lot of the body's processes and important compounds that it needs. In terms of hydrogen bonds, this is one that's unique to hydrogen itself, and especially water is when it's most applicable. So in this case, you see the hydrogens have a positive charge to them, while the oxygen has a couple more electrons floating around. So that gives a negative charge on this side of the molecule, while we have a positive charge on this side of the molecule. So because that's an uneven distribution of the charge, it's considered a polar molecule. And so in water, you have a bunch of these H2Os. So the negative portion of the water molecule that's the portion of the water molecule that's negatively charged can be attracted to that slightly positive hydrogen on another molecule. So all these water molecules bond together in this way, and that gives water a lot of the properties that make it a really, really important thing in our body. But it is a relatively weak attachment because it's only partial charges. All right, this brings us to question 2. What bond occurs when one atom shares an electron with another atom? I know we just went over this, but take a second and think about it. Okay, decovalent would be the correct answer. Remember, they actually share between the two. Hydrogen bonds we just talked about are a weak attraction between the polar water molecules. And then ionic bonds are when there's a full transfer of an electron from one to the other, like the sodium to the chloride example. And then there are all types of chemical bonds. So chemical bonds is a bit of a broad answer in this case. Okay, moving on to energy. Of course, our body needs energy to function. And this energy is stored in the bonds of all these molecules within our body. This is considered potential energy because it's stored. So when a chemical reaction happens, energy is released and it can do work. This is also known as kinetic energy. So the sum of all of our chemical reactions in the body, that's what makes up our metabolism. So that's kind of classified in 2 different ways. You have catabolism, which is breaking down complex compounds into simpler ones. If a catabolic reaction occurs, there's going to be a release of energy. This can occur in the form of heat, but most of it is transferred to ATP, which is adenosine triphosphate, and that's our body's main fuel source. at the cellular level anyway. The other type of reaction you can have in your metabolism is an anabolic reaction that is building larger, more complex molecules from some of the smaller subunits. And so that's going to require energy to do that. And so usually ATP is going to be utilized to power an anabolic reaction. Okay, here's a quick overview of a few types of chemical reactions. All right, so a synthesis reaction, and just to clarify, I don't need you guys to know any specific reactions. Just if you see them in this A to B form, I want you to be able to identify what type of reaction is which out of these ones we're going to discuss in the next few slides. So synthesis, you have two different elements or substances, and they're going to form a new substance. So new bonds are formed, energy is required. So that would be an anabolic reaction. It's going to require energy. A decomposition reaction is kind of the opposite. You have that complex substance, or the AB, is breaking down into its individual parts or simpler parts. So energy is released because bonds are broken. And then, like we said earlier, that could be released in the form of heat, or it may be stored for future use, converted into ATP. And then the last type we have is an exchange reaction. So two molecules are going to exchange atoms or groups. So in this case, A gets the C and B switches over to D. So they kind of swap spots. And then two new compounds are formed. There's no individual parts. Okay, reversible reaction can apply to both or all three: synthesis, decomposition, and exchange reactions. This happens a lot within the body. So in a sense, the reverse of a synthesis reaction becomes a decomposition reaction. A decomposition reversal looks like a synthesis one. And in terms of the exchange reaction, it's just going back to how it originally started. Okay, I think we are going to pause here, and I'm going to end this section of the lecture. We will pick back up in the next recording on inorganic compounds.